So here we discuss more than 1 degree of freedom systems. So introduction to 2 and more degree of freedom systems. So how to get the equations of motion, and then we'll see how to find out the natural frequencies. So the number of natural frequencies is equal to the number of degrees of freedom. So for a single degree of freedom there is a single natural frequency, and for multi-degree of freedom systems there are multiple natural frequencies, and the number of natural frequency is equal to the number of degrees of freedom. Now here we have shown a 2 degree of freedom spring mass system. So on this mass there is a force F1, and on this mass there is a force F2. So this is X1 and this is X2. This spring stiffness is K1 and this spring stiffness is K2. So now if you draw the free body diagram of this, so if it is extended by X1, then the spring above gives the force on it, which is K1 X1, and if X1 is greater than X2, then this spring is compressed, or if X2 is greater than X1, we have assumed here, anything you can take. If X2 is greater than X1, then this spring is in tension and this spring actually pulls this mass. So these are the two forces, K1 X1 and K2 X2 minus X1. We have assumed X2 is greater than X1. So and it is having an acceleration X1 double dot. So and as to have forgotten to show that here there is a downward force F1. So here there is a downward force F1. So there is a downward force which I have forgotten to show, F1, and this force is, and this force is, this force is F1. So now this is the equation of motion. Force, the total net force F1 minus K1 X1 plus K2 X2 minus X1 equal to mass into acceleration in the direction of the net force. So this is the, for this body, this is the net force and this is the mass into acceleration, and this is this. So if you simplify this, you get this. If you simplify this, you get this, and finally you get this equation. And if you write it in matrix notation, this becomes this. So this is the mass matrix, this is the stiffness matrix, and this is the force vector. So for free vibration, this right hand side is 0, so we get this. So here what is done is, since for free vibration, if we excite the system and then let it move on its own, then that is free vibration, then we get an oscillation. So what is done is, a solution is assumed in this form, an oscillatory solution is assumed in this form, where this vector contains the amplitudes. That means this x0 is x10, x10 is the amplitude of x1, that is this x is actually x1 and x2, and x10 is amplitude of x1 and x20 is amplitude of x2. So this is actually x10 sin omega t, x20 sin omega t. And if you replace it here, then you get this equation or this equation, and you know this is a generalized eigenvalue problem, and if you multiply both sides by m inverse, then this. So this is of the form ax naught equal to omega square x naught. This is of the form ax equal to lambda x. This is called the standard eigenvalue problem. So please do not confuse this A matrix with the flexibility matrix, because frequently we denote the flexibility matrix by A. So, and in this A11, A12, A21, A22, x10, x20 equal to lambda, and this is the identity matrix. We can write it like this, and then if you subtract the right hand side from the left hand side, 2, 2, 1, A22 minus lambda to 0. So A11 minus lambda, A22 minus lambda minus this equal to 0. So it has got two eigenvalues, and this 2 lambda 1 and lambda 2, 2 gives you two values for omega 1 and omega 2. So the 2D of freedom system has got two natural frequencies. Also you can directly get the eigenvalues from this equation. This is called a generalized eigenvalue problem. Now the flexibility matrix and the influence coefficients. So suppose take this P1 is a static force applied at degree of freedom 1, and Y1 is a static displacement, and P2 is a static force and Y2 is a static displacement. So for the time being you assume it like this. Then Aij is defined as deflection at I due to unit force at J. So A11 would be deflection at DOF1. So there is a deflection at DOF1 due to unit force at DOF1. So if you give a unit force at DOF1, and then what is the deflection of DOF1? That is 1 by K1. And what is the deflection here? 1 by K1. A21 would be again 1 by K1. And A21 is 1 by K1, because if you give a unit force here, A21 is deflection at DOF2 due to unit force at DOF1. So if you give a unit force 1 here, then this also will move by the same displacement 1 by K1. So this is 1 by K1, this is 1 by K1, and A12 is deflection at DOF1 due to unit force at DOF2. So you notice A12 is deflection at DOF1 due to unit force at DOF2. So if you give a unit force here, then what is the deflection here? So if you give a unit force here, that unit force is transmitted here. So it will be having the same displacement 1 by K1, because both these springs will be subjected to the same force 1. So again A12 will be 1 by K1, and A22 will be, so if you give a unit force here, A22 will be 1 by K1, because this spring is subjected to 1 and this spring is subjected to 1. So the deformation of this spring is 1 by K1 and the deformation of this spring is 1 by K2. So 1 by K1 plus 1 by K2. So this is K1 plus K2 by K1 K2. So flexibility matrix A is A11, A12, A21, A22. So this is this. And if you invert it, then this is this. So when you invert it, this, the sign in the off diagonal terms change and these two terms get interchanged. So this is this and you get this. So you notice that this is same as the stiffness matrix what we got here, the stiffness matrix. So this, and you know that this is the matrix of the influence coefficients, which is also called the flexibility matrix, the matrix of influence coefficients. And inverse of influence coefficient matrix or inverse of the flexibility matrix is nothing but the stiffness matrix. So this is the main thing to learn from this. And now we will study some approximate methods for finding out the first natural frequency, because in mechanical systems the first natural frequency or the fundamental natural frequency, the first natural frequency is also called the fundamental natural frequency, is of more importance, because due to different type of excitations the first natural frequency gets excited. So here we'll be using the Dunkerley's method to find out the first natural frequency. So here you see, if y1 is the deflection here and y2 is the deflection here, then y1 is actually y11 plus y12, that is deflection at 1 due to force at 1 and deflection at 1 due to force at 2. Similarly, deflection at 2 is sum of two parts. One is deflection of 2 due to force at 1 and deflection of 2 due to force at 2. And you know the influence coefficients A11 and A12. So y11 is y1 is y11 plus y12, that is deflection at 1 due to force at 1 and deflection at 1 due to force at 2. So deflection at 1 due to force at 1 is A11 into P1. So deflection at 1 due to force at 1 into P1 and deflection 1 due into force at 2 into force at 2. So this we know that y1 y2 is now A11. So A11 you know deflection at DOF1 due to unit force at DOF1, but at 1 there is P1 force, so A11 into P1 is y11, and y12 is A12 is deflection at 1 due to unit force at 2, but at 2 there is not unit force is there, P2 is there, so A12 multiplied by P2. So if you write it in matrix notation, so this is what you get. Now when this is a case of free vibration, the P1 and P2 are coming from inertia forces. So if you take the downward direction to be positive, then y1 double dot is in this downward direction, y2 double dot is in this downward direction, and the inertia force minus m1 y1 double dot in this direction and minus m2 y2 double dot is in this upward direction. So this is this. So P1 and P2 are nothing but this, and this can be written like this. So again, if you put it here, this P1 and P2 is replaced by this. So y1 y2 is this, or y1 y2 is minus a11 m1 plus a12 a11 m1 y1 double dot plus a12. So here it is a11 m1 and here it is a12 m2 here, A21 M1 and A22 M2 if you multiply these two matrices, and this Y1 double dot Y2 double dot. Again, if you assume that the vibration is harmonic, so Y1 and Y2 is some amplitude capital Y1, some amplitude capital 2. So small y1 is capital Y1 sin omega t, and small y2 is capital Y sin omega t. And if you take this, so this is this. So this is this. So now this sin omega 2, this gets cancelled, and finally we get this eigenvalue problem. And you know, here if we write it like this, ay equal to lambda y, then there are, since this is 2 by 2 matrix, there are 2 lambdas, and the sum of these 2 lambdas is the trace of the matrix, that is sum of the diagonals. So sum of the 2 lambdas are 1 by omega 1 square plus 1 by omega 2 square. This is lambda 1 and this is lambda 2 is the trace of this matrix. And what is this? This is nothing but, if you put, forget about the mass 2, just put mass 1, then what is the natural frequency? That is omega 1 1. And forget about mass 1, if you put only mass 2 on this system, what is the natural frequency? That is omega 2 2. So 1 by omega 1 square, when both the masses are placed, then this approximately, this is the first natural frequency. So here omega 2 is, we assume that the omega 2 is comparatively much larger than omega 1, so this term is smaller. So the left hand side is approximately equal to 1 by omega 1 square. So this is this. So 1 by omega 1 square is approximately equal to this, and this is nothing but 1 by omega A11 M1 is nothing but 1 by omega 1 1 square. That means if you just put mass M1 alone, and if you put M2 alone, so you can write it like this, or you can write it like this. Both forms are useful. So you can write it like this, or you can write it like this if there are n disks. So let us stop here. Next we will see Rayleigh's method, which is again another approximate method like Dunkerley's method, and we will see that the Rayleigh's method also gives you approximate natural frequency. So, and then we'll work out some examples. So let us stop here, and we'll continue in the next lecture.